GCSE Physics boosters, springs. This video is about springs. There's my mate Stretch Armstrong and a dog in the background. Okay, now forces can change the shape of an object. Forces can deform an object. It can be compressed, it can be stretched, it can be bent. Okay, notice that in all of these cases there is more than one force involved, and to change the shape of an object you would need more than one force. If you just pushed an object, then it would move and it wouldn't be deformed probably. So to squash it or stretch it or bend it, you need more than one force. Now, this is an experiment that you should certainly have done, and it is stretching a spring. And what you do is you hang a spring on a retort stand and you put masses on it, 100-gram masses up to about a kilogram, up to 1,000 grams, and you measure the extension. Now, the extension is how much it stretches. That is its length minus its original length. Its extension, little e. We will say, excuse me, we'll say that each 100-gram mass has a weight of about 1 Newton. Okay, it'll actually be 0.98 newtons, but we'll simplify it. We'll say 100 grams has a mass of 1 Newton. So we're going from 0 to 10 newtons, measuring the extension, and we should get a graph that looks something like this. So this is force on the bottom, our independent variable. We've got extension up the side, our dependent variable, and we get a straight line. Now, what does this mean? Okay, by the way, before I say that, if we're actually squashing a spring, if you were putting masses on the spring and it was squashing, then little e would be called the compression. So if you're stretching it, it's the extension. If you're squashing it, it's the compression. So the graph is a straight line through the origin. And that tells us that in this case, the extension is proportional to the force. There is a linear relationship between F and E. Linear, it's a line, a straight line. They are directly proportional to each other. And the relationship is F equals KE. K is a constant, and it's a property of the spring, and it's called the spring constant. If you look at the equation, K would be F over E, so K would be measured in newtons per meter. So little k is the spring constant measured in newtons per meter. Have a go at these questions yourself, pen, paper, calculator, and I'll show you my answers in 3, 2, 1, there. So the first one, this spring, a car's got 4 springs in its suspension, and the mass of the car is 1,800 kilograms, so the weight of the car will be 18,000 newtons. That force will be shared between the 4 springs. So each spring there'll be a compressive force of about 4,500 newtons. The tricky thing here, be careful, is that I've given you the compression in centimeters, but I've asked for the stiffness in newtons per meter. So K is F over E is 4,500 divided by 0.08. So 8 divided by 100, because I want it in meters, not centimeters. And you get 56,250 newtons per meter. In the second example, I'm just using F equals KE. Again, I've given you E in centimeters, so you've got to change that to meters, and you get 24.5 newtons. If you stretch a spring, then you're doing work. In the last video we talked about work. Work equals force times distance. Now, as long as the spring behaves elastically, and we will talk about that very shortly, what I mean by that. As long as it behaves elastically, then it is storing elastic potential energy. So a stretched spring or a squashed spring is storing elastic potential energy. Now, you don't need to learn this equation. It'll be on your formula list. And it is basically that your elastic potential energy is 1/2 ke squared. Let's look at an example. So this pinball machine thing, the mechanism fires the ball. This mechanism fires the ball in a pinball machine. The spring constant is 350. We compress the spring by 7 centimeters. So how much elastic potential energy is it storing? And then when you let go of it, what will happen to that energy? So have a go yourself, and I'll show you the answer in 3, 2, 1. There you go. So the elastic potential energy is 1/2 ke squared. So 0.5 times 350 times 0.07 squared. And if you work that out properly, you should get 0.86 joules. When you let go, and this is the whole point of the mechanism, this energy, most of this energy, will be given to the ball in the form of kinetic energy. Now, elastically, behaving elastically, that means that it returns to its original length. At GCSE level, it also means that the graph is a straight line. So elastic behavior, the spring returns to its original length, the graph is a straight line. If you put too much force on our spring, then it will be permanently deformed. Okay, basically you'll knacker it. And this is called inelastic behavior, or another name for it is plastic behavior. Inelastic behavior, there is a permanent deformation. Okay, there's a permanent extension if you're stretching it, and the graph is no longer a straight line. And if you look at this graph here, you'll see there's a point called the elastic limit. So before the elastic limit, it's a straight line. That's the limit of proportionality is another name for it, because it stops being proportional then. The limit of proportionality. Beyond the elastic limit, then it behaves inelastically or plastically. A little question, one thing you'll probably have to do is read information off a graph. What force causes this spring to behave inelastically? And hopefully looking at it, you should realize that it is 6 newtons. Now, this is very important for engineers. If you're an engineer designing a bridge, then the cables of this bridge, they support the weight of the bridge and of all the traffic on the bridge. And it's very important that you don't go beyond the elastic limit of the cables. Okay, why is it important that the elastic limit of the cables is not exceeded? And it's not so that the cables don't break. I mean, you'll need quite a large force to break them. But if you go beyond the elastic limit, then what's going to happen every time a load of traffic goes over the bridge, the cables are going to get longer and longer, and eventually the bridge is going to sag in the middle, which wouldn't be very good.